and we will see many bat viruses, many coronaviruses from bats. Whether they can cause disease in humans is a good question. Nobody's really knows. But we'll come to that later. So here we have the outbreaks of a number of cases of Ebola virus in these West African countries in 2014, 2015. And the key things about this were, where did this origin come from? It arose around this area here, between Sierra Leone and Liberia, and unfortunately the virus was carried in this direction by one person and to the south by a second person. The outbreak was so devastating because nobody expected Ebola. So by the time people had worked out that it was Ebola, the virus had already taken a foothold, and the second problem was that Ebola had never turned up in this area before, so the countries were not prepared for it. They didn't have the protective clothing, they didn't have health services which were set up to deal with this virus, and they also didn't have the money to do it. So they didn't even have enough bleach to decontaminate clothing or suits or workplaces or even hospitals. So this was quite a tragedy. It did, however, push the world into testing vaccines, because it was clear that this could only be brought under control with vaccines if the measures of quarantine and isolation did not work, and also to prevent people from being infected when the virus was reaching places where it hadn't been expected. And that really pushed the world to develop vaccines, as we'll see in a minute. But I also want to look at another Ebola outbreak, which happened, risk regions for Ebola. These are all risk regions for Ebola, but this one was a big surprise. Here we have different variants of Ebola. This is the most common one. This is the Ebola virus from Zaire. And this is also the one which causes the most disease. All of these areas here are at risk for Ebola. The problem is, what is the host? What is the natural host for this virus? People say it's bats, but the evidence is not convincing, at least to me. It still really needs to be shown. It has been found in bats, but whether it's the natural reservoir is a good question. And then we move to the next outbreak. This data taken from ProMedMail.org. If you give in ProMedMail into Google, you will find this quite easily. This is where I get all my information for, or most of my information for SARS coronavirus 2. And this was an outbreak which started in Beni in the east of the Democratic Republic of the Congo. So this is in the real Ebola country. And this was very difficult to bring under control because this area is under control of many military groups. The government is not really under control here. Many health workers were killed. Many is too many, but several health workers were killed. People were frightened to come to the doctors to check whether they were free of Ebola or whether it was a case of Ebola, and so on. It was eventually brought under control, this outbreak here. This is about 18 months into the outbreak. 3,000 cases, 60% of those were fatal. 5% were health workers, so people sacrificed their lives to try and bring this under control. And very importantly, this epidemic was brought under control eventually with 2 vaccines. The first one, which was used, is this recombinant vesicular stomatitis virus. This is an alpha virus, which we looked at in Principles of Virology. And CVOV means this is the Zaire Ebola virus, and this is the spike protein. This is the glycoprotein found on the surface of the Ebola virus. And this is a virus which expresses this protein and causes a an immune reaction against that protein, which is protective. And the second one here is an adenovirus 26 virus with a modified vaccinia virus. It's a pox virus. And this is one shot of this one. This is an adenovirus very similar to the adenovirus that is being used in the Oxford AstraZeneca vaccine and also in the Sputnik 5 vaccine. So the first injection with this one and then a second injection with this one. And this was also well tolerated and was also used to stop this outbreak of Ebola virus. There was another outbreak of Ebola virus then during 2020, in a little bit west of that, to the northwest. That was also brought under control. And then, very recently, I came across this from ProMed Mail. It's a screenshot. And you can see this Ebola update Guinea. And this is an outbreak in Guinea, again, in West Africa. And again, the spread was brought about because nobody was expecting Ebola again in West Africa. Basically, everybody's looking for SARS coronavirus 2 anyway. So it was a while. The initial patient was diagnosed with malaria, but it turned out not to be malaria. It turned out to be Ebola. And this was worked out because several of the people who attended the funeral also became sick with similar symptoms. And that is not what you would expect with malaria, which is transmitted by mosquito. So where did this virus come from? And it appears that this virus, that Ebola, is asymptomatic in the population. It appears that it's been persisting. If you read this article, you'll find out more about it. And this is a real, I use this word carefully because it's been used so often with SARS coronavirus 2. This is a game changer. That persistent infections with Ebola are possible over a period of several years was never expected before. And that may also change our view about what we're looking for in the reservoir. Maybe this virus is, the reservoir for this virus is humans. It certainly appears to be in this case. So that's something that will be a frontier for a while, is trying to work out how much of Ebola is present in a persistent state in humans. And it's really a call for vaccination of as many people in Africa as possible with these vaccines that we now have available to prevent this virus from spreading. Just to look at the Ebola virus itself, here is the genome. It's a negative strand genome, so it can't be translated directly. It has to be copied by the polymerase, which is in the particle, so the typical negative strand non-segmentic virus, with a polymerase which has a cofactor from the viral genome. Very long virus. It looks, even in this cartoon, quite frightening. And this is the glycoprotein. This is the spike which is used in the vaccines. And then there is a matrix protein here in brown and the nuclear protein bound to the RNA. Quite straightforward virus. And the transmission between humans via contact with infected body fluids, but it's possible that this person who was infected in January in 2021, that this was a sexual transmission. Not clear, but it certainly was not transmitted by somebody who was clearly Ebola positive. The natural host is clear. The transmission within that natural host is not pathogenic, so that's why we can't find it. And as I said, some evidence that bats are the natural host, but the data is not conclusive. So we leave Ebola and we move to coronaviruses. Here, I'm sure you've seen this picture several times, maybe certainly in my lectures, but something similar in newspapers and something like that. Here we have the coronavirus, the typical corona-like shape of the spike protein. Here the schematic, here is the spike protein. Here are the M and E proteins in the lipid bilayer. And then we have the RNA, which again is bound by a nuclear protein. Very unusual virus. It has a positive strand, so the RNA can be translated immediately, but the RNA is bound by this nuclear protein. very uncharacteristic. And the symmetry of this viral capsid, or this viral genome, is helical and not icosahedral, which is generally the case for positive strand RNA viruses. We look at the genome. We have the positive strand genome, 5', 3'. So when it enters the cell, when the virus enters a susceptible cell, there is translation of the 1A open reading frame and the 1B, 1AB, which gives rise to the 1A protein. There is a frame shift here at the end of the 1A open reading frame, which allows the ribosome to shift backwards one and then go into the next reading frame, which gives us 1B. And so initiation of translation at this AUG can give rise to generally 85% the 1A protein and 15% the 1AB protein. Within these two polyproteins, there are proteases which can cleave these polyproteins into the mature proteins, the most important of which is the viral RNA polymerase. But there is also a viral protein which does proofreading. Remember, this genome has around 30,000 nucleotides. It's 3 times the length of the average an average positive strand RNA genome. So the virus is including a proofreading enzyme in its polymerase complex to increase the fidelity of transcription or copy of replication, so that the virus does not produce too many mutations. But as we've seen with SARS coronavirus 2, mutations are very important. The first thing that happens in terms of replication once these two proteins have been translated and processed is that the positive strand RNA is copied into a full-length negative. And then the virus starts to produce subgenomic mRNAs, starting here with this leader sequence. It can produce a full length, but it can also produce subgenomic by jumping here and then starting again here to produce an mRNA, which will be used for open reading frame 2. And then another one where it jumps further down to produce open reading frame 3. These mRNAs will only be read for one open reading frame, because in mammalian cells, once the protein has been translated and the stop codon has been reached, the ribosome falls off. So these viruses produce a lot of subgenomic mRNAs. These proteins here include M and E, but there are several open reading frames, and these open reading frames really differ amongst coronaviruses, and they differ within the genus to which SARS coronavirus 2 belongs, sarbecoviruses, enormously. So some open reading frames are missing, some are more, some are different in sequence, and so on. And the other thing about this mechanism here, this very unique springing of the polymerase across here to produce these mRNAs, this ability of the polymerase to stop and start again on different places, also leads into the idea of recombination. And we have seen from the number of bat viruses sequenced and from other animals that coronaviruses are world champions in recombination, and that is one of the reasons for the appearance of SARS coronavirus 2 and probably SARS in 2013 as well. So we'll come back to the mechanism of recombination in coronaviruses later in lecture 3 or lecture 7, but we continue here with an overview of SARS coronavirus